And good evening, everybody, to everyone out there, the more than 4,000 of you joining us tonight. Welcome to Online Prep Live for the ACT with Kaplan. My name is Arthur On, and I'm a Kaplan ACT instructor. It is my privilege and honor to be with you this evening as we go through our introduction of ACT STEM concepts. So in our first hour, we're going to look at some of the math concepts for ACT success. And our second hour, we're going to look at the science test for the ACT. Again, my name's Arthur, and I am joined by a all-star team of fellow Kaplan ACT instructors, Kristen, Liz, and Rob. You'll be interacting with them through the chat, which I know a lot of you guys are having some fun with right now, and also, even more importantly, with the poll questions as we bring up practice questions. As we're going through the problems, click on the answer that you think is right so that we can make sure that everyone's on the same page, that we're interacting well with you guys. And if you have any questions or any comments, bring those up into the chat as well. So in our first hour of tonight, we're going to look at the introduction to the ACT math test. And we're going to look at 4 learning objectives this evening regarding math. First, how to look at those linear and quadratic equation questions, how to look for proportions, ratios, and rates to find those unknown values, how to find the area of circles, rectangles, parallelograms, things like that. And lastly, how to use information in geometric shapes to calculate missing sides or missing angles or things like that. So really quickly, just to summarize what the ACT math is all about, if you notice what we see here, it says that the ACT math test includes 3 subscores based on those 6 content areas. And you may be looking at those content areas like, whoa, some of those look a little bit trickier. Some of those are a little bit more difficult than others, but not to worry, because nearly half of the test is on pre and elementary algebra, and barely a quarter of the test is on geometry and trigonometry combined. So don't worry that some topics may be a little bit more difficult than others, but don't think that the ACT is just trying to throw random math topics at you. Instead, the ACT math test is basically just seeing if you can apply basic formulas, and more importantly, if you can apply reasoning skills. And I see a lot of great questions right now, whether you need a calculator tonight. So for the purpose of the ACT, a calculator is allowed, but here's the good thing. You actually do not absolutely need a calculator on the ACT. All of the math problems can be solved without using calculator. But please feel free to have a calculator nearby as we go through some of these practice questions. Also remember, the math test is always the second test on the ACT. It will come after the English test. It will come before the reading test. The math test is 60 minutes long and has 60 questions. You may be thinking to yourself, well, that's kind of easy. 60 minutes long, 60 questions. That's probably 1 minute per question. But also think about those topics that we just saw. If there are certain topics that you feel stronger on, see if you can answer those, not in 1 minute, but maybe a little bit less than 1 minute, like 45 seconds or 40 seconds. That way you can save that extra time for that tougher geometry question or that tougher trigonometry question. So just think in those terms, 60 minutes, 60 questions long. So let's get started with a couple of key algebra concepts, starting with stuff that you might remember, not even from high school, but from way back when. Manipulating variables in linear equations. The first thing we'll always want to remember, if you are dividing by 3 on the left side of the equation, or you're adding 5 to the left side of the equation, always remember, do the same thing to both sides of the equation. This way you maintain the equality and you can still manipulate the numbers. Now the next thing, and tell me in the chat if you remember a certain mnemonic device or a way to remember what the order of operations refers to. What the order of operations is which step you do first to simplify the calculations. But a lot of you might remember a certain mnemonic device to help you remember, help you keep track. And for whatever reason, the last part is always, well, if you remember the mnemonic, and you can let us know if you've seen this before, please excuse my dear Aunt Sally. Let us know if that sounds familiar. For some reason, it's always Sally. It's never Stephanie. It's never Susan. But this is the order of operations. First PEMDAS, then exponents, then multiplication and division, and then addition and subtraction. And remember, when you're doing multiplication and division, these two, it's not that multiplication comes first, it's that whichever goes left to right first. And then for addition and subtraction, same thing. It's not automatically the addition sign that comes first, it's whatever is left and then going right with that equation. And then lastly, if you remember, good old distributive property. We have something outside the parentheses and you're multiplying it by something inside the parentheses with an addition or subtraction sign. Multiply everything outside the parentheses by everything inside the parentheses. So A times B and A times C will give you the AB plus AC. Let's take a look at an example of how to apply some of these skills for a question dealing with linear equations. And as you're reading this question, you may notice, wait a minute, if you look at the wording there, the wording at first may look even a little bit abstract. But if you want to put into the chat just to make sure we're on the same page, what is this question really asking you to find? Like don't get thrown off by the weird wording. But really what this question is asking you to find is simply this. What is the value of z? So we want to take that equation, which we're going to rewrite over here, and find what that value of z is. So the next step, notice you have this subtraction sign in front of the parentheses. Subtraction sign in front of the parentheses. So if you have a subtraction sign there, remember to change the sign of everything inside the parentheses. So you notice how that plus 5 became a minus 5. Okay? So 3z minus z over 2 minus 5 is equal to 10. Well, the next step is this. Well, if I want z equals something, let's get the z's together, and let's get everything else on the other side. So we're going to move that negative 5 over. So we've got 3z minus z over 2 is equal to 15. And then from here, find that common denominator so we can combine these terms together. The common denominator is going to be 2. So that 3z becomes 6z over 2 minus z over 2. And if you remember, subtracting fractions with the same denominator means that we'll have, we just combine the numerators together. 6z minus z is equal to 5z over 2 is equal to 15. I think I'm seeing some people put it in. Again, if you have an answer, put it into the poll, but I think a lot of you guys are getting to it now. The next thing we do, get rid of that denominator, multiply by 2. That gives us 5z is equal to 30. And our final step, well, to get z by itself, got to divide by 5. Z is equal to 6, and we're done. D for done is your correct answer. So great work on this question. As we see, we just want to find what z is. And remember that one thing, when you have the parentheses and using the distributive property for everything inside the parentheses. Our second concept dealing with algebra talks about quadratic equations. How to solve for those equations where if you have like an x squared term or something raised to the second power. So to create a quadratic equation, you remember this from way back when, use good old FOIL, which refers to first, outer, inner, and last. So if you see those terms there, the x and the x are going to be x squared. The outer terms, x and negative 3, will give you negative 3x. The inner terms, positive 2 and x, will give us 2x. And then already you might be thinking, wait, I can combine those two. Negative 3x, positive 2x will give you the negative x. And then the last terms, positive 2 and negative 3, negative 6. So that's how we use FOIL to multiply out those equations. FOIL is basically just an example of distributive property. Now, what if you have a quadratic equation and you want to factor that? Well, we factor by using reverse FOIL. So if you take a look at this example here, x squared plus 5x plus 6 is equal to 0. Always remember, when you're trying to factor, make sure that equation is set equal to 0. And now that it's set equal to 0, we're going to do two things. The first terms, well, what two terms, when we multiply them together, get us x squared? That's the easy part, right? The x and the x, right? So you plug in the x and you plug in the x. And then the second step is this. Look at the constant, that last term, and look at the coefficient of the middle term. And always ask yourself this. What two numbers multiply together to get you the last number, the coefficient, the constant, and add up together to get you the coefficient? What two numbers in this case multiply together to get 6 and add together to get 5? And it's going to be plus 2 and plus 3, and boom, there's your factored formats. Okay? So let's take a look at a question of how we can apply this as well. Take a look at the second example. The question here is asking us for the sum of the two solutions for x. And be careful here, because if you notice, this question is not asking you for what x is. It's asking for the sum of the two answers for x? Well, we've got our quadratic equation here. X squared plus x minus 56 is equal to 0. So we're going to use reverse FOIL here to find what x is. The purpose of getting that equals to 0, we'll see in a second, but that basically gives us an idea of what x is once we find the factors. So let's break those up. We have the x, and the x will give us the x squared. And then what two numbers, in this case, do you multiply together to get negative 56 and add together to get plus 1 or positive 1? And in this case, if you notice, we've got x minus 7 and x plus 8. Negative 7 and positive 8 will add together to get positive 1 and multiply together to get negative 56. So if we know these two factors multiplied together equal to 0, then we set each of those individual factors equal to 0, and we've got x is equal to 7 and x is equal to negative 8. But wait a minute, are we done? Oh, this question's not asking you for what x is. If it did, there would actually be two answers. And the ACT will never do that to you, where the two answer choices are the same. They will not try to throw you off like that. The question is asking simply for the sum of the two solutions. And as we see here, well, the last step, add up those two numbers. 7 plus negative 8 gives you negative 1. Answer choice H is your correct answer here. So remember to practice how to reverse FOIL. When you see that quadratic equation, think, how do we break those up into those two factors? Great work for those of you who got this question correct. And just be careful here, because again, there's a lot of wording here at the very beginning of the question that can throw you off a little bit. So we see about 40% of you got this one right. Slightly higher than the majority got this one wrong, so be careful there. Notice the part of the question might have thrown you off a little bit. I think it's that first part, which says the sum of the two solutions, and also remember to practice the reverse foiling. Okay? All right, let's take a look at our next concept, which deals with proportions and ratios, and how to use proportions and ratios to solve for unknowns. So ratios and proportions, and sometimes you might remember from way back when the formatting of A colon B, but A colon B doesn't do anything for you mathematically. So it's basically easier to just write it out as A over B. A divided by B, write it as a fraction. And there are two things you always want to ask yourself. One, is this a part-to-part question or a part-to-whole question? For instance, is it asking me to compare dogs and cats? That would be part-to-part. Or is it asking me dogs and all the pets? Notice I wouldn't say all the pets, that's like a total. So is it a part-to-part question or a part-to-whole question? And secondly, is the question asking for a new ratio or is it asking for a total number? Okay. If you only have a ratio, you can find its multiples, but not an actual total. So for instance, I know we've got a whole bunch of people in the room right now, almost 6,000 of you guys. But if I were to just say, well, if I don't know what the number is, right? If I just say for every 4 boys in this room, there are 5 girls. Do you know for sure how many people? You might be thinking, well, isn't it just 4 plus 5, which is 9? But a ratio only gives you the potential multiples, not the actual total. But if I say, well, there are 4 boys and 5 girls, if the ratio is 4 to 5 for boys to girls, but I tell you there are 40 boys, then you know for sure there are 50 girls, because you would apply the same multiple to each part of the ratio. Let's take a look at an example of how this is applied. Take a look at number 3. The value of S is directly proportional to the value of T. So stop right here. When you see the word directly proportional, I want you to immediately think, all right, I'm going to set this up as 2 fractions that are equal to each other. That's what directly proportional basically means. 2 ratios equal to each other. When S is equal to 9, T is equal to 36. All right, well, they tell us S and T. These are 2 different parts of the ratio. So what is S when T is equal to 30? Well, let's set up that ratio, or let's set up that proportion, rather. If S is equal to 9, T is equal to 36, that's where we get the 9 over 36. And since the question is asking us for S and we're given T, we can apply that question apply the proportion to say S over 30. So that's the first step here. Then after that, well, how do we simplify an equation when we've got fractions? And you might remember the good old math term for this, referring to cross multiply. And here's where you absolutely should use a calculator. I do not want anybody in this room multiplying and dividing out the terms that we're going to see here. But we've got 36s is equal to 270. And then from here, to figure out what s is, we're going to divide by 36. 270 divided by 36. I'm seeing a lot of answers here. 270 divided by 36 is equal to 15 over 2, which is answer choice B. B is your correct answer here. Okay. So when you see the question says directly proportional, think to yourself, all right, directly proportional means I'm seeing two things that are equal to each other. Set up two ratios equal to each other. Great work on this question. 88% of you knocked this one out of the park. 15 over 2 is your correct answer. One quick logistical thing as you're watching this right now, you can set your video to a higher quality if you click on the gear icon. I believe it's on the bottom, towards the bottom of the screen. If you want to increase the, I forget the technical term for it, to make it higher resolution. If you're having any trouble seeing the questions or the animations on the slides, you can click on the gear button there, and that'll increase the quality of the video. So definitely check that out. We definitely want to make sure you're understanding what we're seeing here and not getting too confused, hopefully. All right, one more algebra concept before we shift gears and look at geometry. And this deals with rate questions. Rates can be any proportion of one unit to another. For example, one of the most common rates, just anything out there, deals with speed. Speed is a rate. Distance divided by time refers to a rate. Distance divided by time is the speed. So for instance, 60 miles per hour. That's a speed, right? 60 miles per hour. That means 60 miles divided by 1 hour. That's a rate. So speed is equal to distance divided by time. But if, let's say, you needed to find what the distance is, take the speed and multiply that by the time. Or if you want the time, let's say, oh, I went 60 miles and I went 30 miles per hour. Well, 60 miles is the distance, 30 miles per hour is the rate. 60 divided by 30, oh, I went 2 hours for the time. Okay, so remember to use these rate calculations when you're looking at those sort of questions. Okay, let's take a look at an example here. Take a look at number 4. And as you're reading through this question, you might notice a key phrase very similar to the previous question here. Very similar to the previous question, and it is the phrase directly proportional. I see a few people mention that in the chat. Directly proportional. So it says the time it takes to complete a job is directly proportional to the number of units produced. Okay, so I've got these two things, right? Time and number of units. If it takes 22 minutes to produce 18 units, how many units are produced in 33 minutes? If you have an answer, click on the correct answer in the poll that you should see on the screen, but let's work through this together. So if you notice it says 22 minutes to produce 18 units, that's an example of a distance and the amount of work that's done, 22 over 18, and that's going to be proportional. So again, we're going to set up two ratios together, and there we have it. 22 minutes over 18 units, 33 minutes over U units, setting up that variable for U. And from here, well, same thing like we did in the previous problem. Cross multiply here. We've got 22U is equal to 33 times 18. And 33 times 18, if you do it in your head, is what? Is what? Wait, what? Please use a calculator for this. Please use a calculator for this. 33 times 18, and then we're going to divide that by 22. So 594 divided by 22, which is equal to 27, and booyah, choice G. For great job, everybody. G is your correct answer. Well done to 90% of you who have put down choice G. One helpful thing to remember is that on the ACT, no formulas are provided on the ACT. So I know it would be a lot easier if you're like, well, if I knew what that rate was, I can always look back at in the test booklet. You will not be given these formulas on the math test. So want to make sure you spend some time reviewing what these formulas mean and how to apply these formulas in the most effective way on test day. All right, great job so far with the algebra stuff. You guys are keeping things lively in the chat. Again, Liz and Kristen and Rob are there for you guys if you have any questions so far. But now let's take a look at some key geometry concepts on the ACT. The first big geometry concept deals with triangles. And again, a lot of this stuff is basically meant to be a review. So the topics and the concepts that we're looking at, again, you've probably seen these at some point, but these are the important things to remember as you're going through geometry questions. First part, a triangle has 3 angles, and those angles will always, always, always add up to 180 degrees. If they don't add up to 180 degrees, it's not a triangle. It's some weird shape from outer space. It makes no sense. So angles in a triangle always add up to 180. You might remember this good old formula about the area of the triangle. Area of a triangle, multiply the base and the height and divide by 2. Or another way to phrase that, 1/2 times the base times the height. Thirdly, you might remember this good old formula, a squared plus b squared is equal to c squared. One important thing to remember, this equation, the Pythagorean theorem, refers to all right triangles and only right triangles. A and B are the legs of the right triangle, and C is that fancy word, the hypotenuse. Basically a fancy word for the longest side in a right triangle. And you'll also want to remember the special right triangles, 3, 4, 5, 5, 12, 13. These are little shortcuts, basically, if you don't want to calculate the math. Like if you get a side that's 25 and another side that's 60, you might be thinking to yourself, well, 25 squared plus 60 squared, I'm going to have to punch in those big numbers into the calculator. But if you can remember, wait, that's a multiple of one of these special right triangles. That can be a quick shortcut for the calculations. Let's take a look at an example here. Take a look at number 8. Question asks us for the degree measure of the smallest interior angle of that triangle. And notice we've got these 3 different angles here. The x plus 2, 4x plus 16, and 2x plus 15. Well, we just said every triangle, the angles must add up to 180 degrees. So let's use that information and set up our first step. X plus 2, 2x plus 15, 4x plus 16 is equal to 180. And at this point, it becomes a more straightforward algebraic exercise. Get the like terms together, the x, the 2x, and the 4x. Get the constants together, the 2, the 15, and the 6, and the 16. We've got 7x plus 33 is equal to 180. Subtract 33 on both sides. You guys know how to do this stuff, right? Subtract 33. 7x is equal to 147. And if we divide both sides by 7, and I'm seeing some really great results in the poll right now, because if you solve for x in this one, x is equal to 21. And notice 21 is an answer choice. But what is the question asking you for? This is the difference between someone who is not quite so careful and maybe someone like you who you're going to make sure that you're answering the right question. This is called strategic thinking. Thinking through what is it the question's actually asking me for. The degree measure of the smallest angle. Now, if you look at those 3 angles, maybe you can type this in the chat if you see it, just not even visually, but if you look at those 3 terms, x plus 2, 2x plus 15, 4x plus 16, logically, one of those angles is going to be the smallest interior angle, and that's going to be the one that's x plus 2. So x plus 2 is going to be our smallest angle. So we know that x is equal to 21. We plug in the 21 for x. 21 plus 2 is equal to 23. Answer choice G is your correct answer here. So be careful about the information in the question and the information in the diagram. Utilize the diagram and what you know about triangles, or as we'll see in a second, other types of polygons. All right? Looks like you guys are doing great so far. Again, let us know if there's anything that needs extra clarification, but you guys are doing great right now. Let's take a look at our next concept, which deals with parallelograms. So a parallelogram is an example, is a figure where you have two pairs of congruent sides. So in this example, notice the sides that are labeled B are the same, and of course the two sides labeled with the A are also the same, A and A. Now, not only do you have two pairs of congruent sides, you also have two pairs of congruent angles, and all of the angles in a parallelogram must add up to 360 degrees. Now, the other important thing to remember about a parallelogram, and this is really important, but if you're looking for the area of the parallelogram, I can't tell you how many students that I've worked with that have said, yeah, multiply A times B, right? No, the area of a parallelogram is the base times the height. The height will always be the straight line distance from the top to the bottom. So if you look at that diagram there where we see the height, notice how the height is perpendicular to whatever the bottom is. So base times height will give you the area of the parallelogram. Okay? All right, so let's take a look then at an example of how you test parallelograms. Take a look at number 9. And you notice in this question, they give us the parallelogram. They also give us ABE is a right triangle. And they're telling us the area of the shaded region, AECD. Now, if you look at that figure, AECD, it's not one of our nice figures. Some of you who are maybe a little bit more advanced in the math, you might recognize that as a particular type of figure, and we're actually going to get to that in a second, referring to trapezoids. But forget that for a second. Like, the trapezoid looks really weird because there's actually a lot of things there's some things we can't figure out about that trapezoid right now. But there are a couple of things we can figure out about the parallelogram and the right triangle, because those are the figures that are mentioned in the question stem. Parallelogram ABCD and triangle ABE. So we want the area of the shaded region. Well, the whole thing is the parallelogram. So let's figure out that part. Area of the parallelogram is equal to base times height. Now again, be careful. The base is 13. The height is 6. Not 10, but 6. So the area of the whole thing is 78. The whole thing is 78. Now, here's the thing. We know that that's the area of the entire parallelogram, which is 78, but we also know the shaded region is going to be a little bit less than the entire parallelogram. And you might notice you can actually get rid of a few of answer choices in that way because it doesn't logically make sense here. Now let's take a look at the triangle. And notice, not only do we have a triangle, we have a special right triangle, where if one side is equal to 6 and the hypotenuse is equal to 10, you can apply the Pythagorean theorem, but if you notice the special right triangle, what does that missing side have to be? Notice it falls in the pattern of the 3, 4, 5. So if one side is 6 and the hypotenuse is 10, that missing side has got to be 8. So we're going to find the area of that triangle, 1/2 times the base times the height, 1/2 times 6 times 8. That's equal to 24, but we're not done just yet. We need to find the area of the shaded region. The shaded region is everything is the parallelogram except for the triangle. So what are we going to do with these two numbers, the 78 and the 24? If you have it, feel free to type it into the chat so we can make sure that you're seeing that you're on the right track here. What do we do with those two numbers? We subtract them. 78 minus 24. We subtract 24 because we're getting rid of the right triangle. And once we get rid of the right triangle, that leaves us the shaded region. Choice C, as 75% of you have put down, is your correct answer. Great work on a relatively higher difficulty geometry question. Remember the formulas for area of parallelogram, area of a right triangle, and when you see these sort of questions, we're talking about like shaded region or things that are missing. Find the area of the entire thing first. Find the area of the entire thing first, and then find the area of the thing you want to get rid of. Find the area of the thing you want to get rid of, and then subtract, because once you get rid of that thing, whatever that is, in this case, it's the right triangle, then you're left with the shaded region. You're left with what you're trying to solve for. I know a lot of you guys are worried about pacing. So one of the things that we just always want to impress upon you guys is even throughout this lesson, if there's certain topics that you feel pretty comfortable with, don't neglect those topics. Improve your pacing even on those topics that you feel relatively strong on, so that it banks more time for you guys to work on a higher difficulty question, okay? And remember that we will have a video. You can rewatch this video later on. This video will be uploaded later on as well. So if there's like 1 or 2 steps that you weren't 100% sure of, don't worry. This is not meant to be like, hey, if you can't answer this question right now, then you're not going to do well in the ACT. This is meant to just be a review of some of those fundamental concepts, okay? But you can always review this later on as well, okay? Let's take a look at our next key concept, dealing with rectangles and squares, other types of figures. So rectangles and squares also have 4 angles that add up to 360 degrees. The one thing to remember is that rectangles have 2 pairs of angles, 2 pairs of sides that are the same, and all the angles are right angles. So 4 right angles each equaling 90 degrees. And a square, same thing with the 90 degrees, but all the sides are the same. The area of a rectangle is found by length times the width. And squares, again, being rectangles 4 equal sides, let's take a look at a question about the work between a rectangle or some other quadrilateral or rectangles, squares, and things like that. Take a look at number 10. Notice here number 10 gives us, again, a very similar concept to what we saw in the previous question. Point A on square ABCD is at the center of the larger square EFCG. So A is right in the middle, right there. DG is equal to 8. What is the area of the shaded region in square inches? So what do we know for sure? We know that DG is equal to 8, so we can label that, absolutely label that. But what else do you notice here? There's a reason why they tell us point A is the center of the square, the center of that bigger square. Well, if it's at the center, or literally right in the middle, well, that tells us some information about the rest of the figure. And if you notice here, wait a minute, doesn't that mean that CD is equal to 8, AD is equal to 8, AB is equal to 8, BC is equal to 8? All these sides are the same in that inner square. So the next part, we want the area of the shaded region. So the shaded region is basically, well, I need the area of the bigger figure, and I want to get rid of the area of the smaller figure. So let's think about what the area of the bigger figure is. Notice how it's square ABCD, center of the larger square EFCG. So these are actually both squares. But if we know one side of this square, notice it's 8 for the first half and 8 for the second half. What are the sides of the larger square going to be? They're all going to be 16. So therefore, we have enough information to figure out what the area of the larger square is. The area of the larger square, 16 times 16, which is 256. Now we need the area of the smaller square, which is going to be 8 times 8. 8 times 8, which is 64. But be careful. 256 is not what we're looking for. 64 is not what we're looking for. It's the area of the shaded region. How do we find the area of the shaded region? What do we do with these numbers again? Same thing that we saw before. We're going to take those two numbers and subtract them. 256 minus 64 is equal to 192. And I see almost 90% of you eventually got to this point. Choice H is your correct answer. Great work on this question. So again, look at the squares. Remember, the square means all sides are the same and all angles are 90 degrees. If you need the area of a square, it's just that same side squared. You're just multiplying that same number by itself. Great stuff here. Couple more concepts. We saw an example of this a little bit earlier about another interesting type of figure called the trapezoid. So in a trapezoid, the bases, call this base 1, call this base 2, they're not the same length. They're never the same length, but they will run parallel to each other, so you'll have one set number for the height. The area of the trapezoid is always found by doing this. First, add up the bases, multiply that number by the height, and then divide that by 2. So area is base 1 plus base 2, whatever that sum is, multiply that by the height, and then divide that by 2. That will give you the area of the trapezoid. So let's take a look at an example of how we can find the area of a trapezoid in a question like this. And if you look at that figure, you're saying, well, if I need the area of the trapezoid, Arthur, didn't you just say, well, I find the bases and the height? Well, I know what the height is. The height is over here, 12. Remember that the height is the straight line distance from the bottom to the top. So the height is going to be 12. One of the bases is labeled as 6. But then you're like, uh-oh, what's this other base? Oh, man, this is going to be the tricky part. Can't figure that out. We need that in order to figure out what the area is. But do you notice here that a trapezoid is actually an example of two figures, in this case, two figures smushed together in a way? If you notice here, the trapezoid is basically going to be using something with a right triangle. If we draw this straight line, and Melanie, I see that you put that, you got the formula there. If we draw the straight line down there, that's 12. And notice this is a special right triangle. We saw this before. If the hypotenuse is 13 and one of the sides is 12, what's this side going to be equal to? This side is going to be equal to 5 using our special right triangles. So we know that little part there is going to be equal to 5, but we need the entire base, right? We need the whole length there. So not only do we have the 5, but notice we have the 6 up here, and that's going to match the 6 down there. So what is the base, the second base, going to be equal? 5 plus 6, which is equal to 11. We've got our two bases, we've got our height, and then we use our trapezoid formula, 1/2 times 6 plus 11 times 12. And we simplify those, we get 1/2 of 204. 1/2 of 204 is answer choice A, 102 as your answer. Choice A for awesome work on this question. I see Owen kind of phrase this a little bit differently, and if you think about it, you can actually do it this way as well. So great point that you made there, Owen. If you break up the trapezoid separately as a right triangle and a rectangle, if you were to find the area of the right triangle and the area of the rectangle, well, what do you do with those two numbers? You would add them together to find the area of the trapezoid. So if you're good with formulas, this is the formula for area of a trapezoid. But as another way to approach the problem, you might want to say, well, wait a minute, can I chop this up? And I think that's what you're saying there, right? You can chop this up to basically find the two different figures and find the areas of those two. Kaplan, Pythagoras, my dude. I love it. I love that. Pythagoras is my dude. Pythagoras must have been a smart guy to one day just be sitting back and be like, hey, I think I figured out this thing about right triangles. And you imagine everybody there was like, ha, 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 that's really funny. Imagine that we're all talking about Pythagoras hundreds and hundreds of years later. So he's a pretty good dude. All right, great stuff so far. Let's take a look at a couple more geometry concepts, starting with circles. Oh boy, circle questions. A lot of times people remember the thing about about pies and all that stuff. But even before we get to that, the radius of a circle is the distance from the center to any point on the circle. Any point on the circle. So that's why circle is the way it's shaped. From the center to every part will be the same. And you might remember some of these formulas. The diameter, if you think about it, is from one edge of the circle through the middle and through the center and then to the opposite. So you're drawing a straight line through the center of the circle. The diameter of the circle is twice the radius, right? If you visualize it, right, diameter is basically one radius and another radius. Two radiuses. I know it's called radii. I know it's called radii, but I like to say radiuses because it sounds weirder. So that's the diameter. Diameter is equal to 2r. The circumference is basically just circumference is essentially a fancy word for the perimeter of the circle, the distance around the circle. Circumference is equal to 2 times pi, and all y'all remember pi, right? 3.14. For the purposes of the ACT, really all you need to remember is 3.14. And for most questions, actually, you can just leave pi as it is. Don't mess with pi. Don't mess with pi. Just leave pi where it is. Circumference is equal to 2 times pi times the radius. So that's the formula for the distance around the circle. And then the formula for the area of the circle is area equals pi times the radius squared. The radius squared. So I see a great example of a formula: x minus h squared plus y minus k squared is equal to r squared, where the center is hk. That specifically deals with coordinate geometry. We're not going to use coordinate geometry in this particular session, but if you have a good understanding of that formula, that's going to be great as a next step for you in terms of mastering geometry in the ACT. So really, that's an amazing formula that you guys came up with there. All right, let's take a look at an example of how circles come together. Two circles have diameters in the 2-to-1 ratio. So again, going back to even something we saw earlier about ratios, be careful. This doesn't mean that the diameters are exactly 2 and 1, right? It's a 2-to-1 ratio, which means one of them is essentially double of the other, right? So two circles have diameters that are 2-to-1 ratio. We're given the area is equal to 36 pi, and we want to know how much larger, and even notice the word larger is italicized, right? How much the word larger is italicized. How much larger is the area of the larger circle than that of the smaller circle? So let's think about this for a second. If we have the area of the larger circle and the area of the smaller circle, so I'm going to make my hand big for the larger circle and smaller for the small circle. If I want to know how much larger is this than this, again, it kind of goes back to one of the things we saw before in some of those other geometry questions. I'm going to leave that thought in your head as we go through the mechanics of this problem. So one of the first things that we're given, is that we have an area. And remember, our formula for area is equal to pi r squared. Well, in this question, we know the area. The area of the smaller circle is 36 pi. So we can apply that in our formula. The area of the smaller circle is 36 pi, and 36 pi is pi r squared. Well, wait a minute. I got an equation here, right? So if the pi's are the same, you can cancel out those delicious cherry or apple or my favorite blueberry pies, and we get r squared is equal to 36. And if r squared is 36, how do we find what r is? Take the square root of that number. And r is equal to 6. Now, those of you might be like, well, wait a minute, isn't it 6 or negative 6? Well, there's a logical reason why we don't have to worry about the negative 6, because if you're talking about geometry, you're talking about distances, right? And distances will always be positive. I hope you've never said, a distance is negative. I hope you've never said, like, hey, how do you get there? Oh, you walk positive 5 blocks this way, you make a left, and you walk negative 3 blocks. Like, what's a negative block, right? So distance will always be positive, right? So r is equal to 6. So we've got that. Now, going back to the original question, though, two circles have diameters in the 2-to-1 ratio. So we know that the radius of the smaller circle is 6, but we have to think in terms of diameter here. What's the diameter of that smaller circle? Well, we're going to double the radius. So the diameter of the small circle is 12. And it says the two circles have diameters in the 2-to-1 ratio. So since the smaller circle's diameter is 12, what's the diameter of the larger circle? And I see a lot of people mention the double thing, so it's going to be 24. So the diameter is 24 of the larger circle. Then we need the area of the larger circle. The radius of the larger circle is going to be 12. And then to find the area, it's going to be 144 times pi. Are we done? Choice H gives us the area of the larger circle. But this is the difference between a common test taker and a great strategically thinking student who's seeing the information and knowing how to answer that question correctly. What do we need to do to find how much larger is the area of the larger circle than the small circle? Take the areas of the two circles and subtract them. 144 pi minus 36 pi is equal to 108 pi, and answer choice J is your correct answer. Okay? Kudos to the 40% of you who got this one correct. This is a tougher question because there's a lot of wording that's going on. So if you need to, again, remember those formulas. If you need to draw a circle, like a smaller circle and a larger circle to help you visualize that, you can absolutely do that as well. Be strategic about the information that's given and how to apply that information. And remember the formulas for circles. Area of a circle, pi r squared. Circumference of a circle, pi times d. Pi times diameter, or 2 times pi times r. I think I saw a few of you mention this in the chat, but a nice little mnemonic device, if you remember, you might have used this in the past, but a nice little mnemonic device to use would be this. Circumference is equal to pi times d, and area is equal to pi r squared. So if you see cherry pie's delicious, that would be the way to remember the circumference formula. Cherry pie is delicious. And then, of course, the other part, which would tell you apple pies, if you say area is equal to pi times r squared, apple pies are 2. Cherry pie is delicious, apple pies are 2. Emma, I would love a piece of pie after class. Let's keep our focus here on the stuff that we got. And remember, guys, after this session, we've got another great session dealing with ACT science as well. So hold off on the pie making for now. Much appreciated, though. Let's take a look at another set of concepts dealing particularly with a little bit more advanced stuff: perimeter, volume, and surface area. Now, we're going to see these formulas on the screen. I don't want you to get consumed about memorizing each of these formulas right this second. But these are the volume formulas to remember. Volume is the space inside a three-dimensional figure. Rectangular solid is given there as volume is equal to the length times the width times the height. The sphere, the volume of a sphere. If you remember what a sphere is, it's basically, if you think about it, it's a three-dimensional circle, basically, a three-dimensional circle. Okay, so sphere, volume is equal to 4/3 pi r cubed. Cylinder is the volume of a cylinder is pi r squared times the height. And the cone. A cone is, if you think about it, almost like a triangular thing where the bottom is a circle and the top is a very small circle, right? So that's an example of a cone. For instance, like a traffic cone, like one of those orange traffic cones that you see sometimes when they're doing like construction on the roads. That would be an example of a cone. To find the volume of a cone, 1/3 pi r squared times the height. So if one thing to remember is, well, if you notice how, for instance, a cylinder is pi r squared times the height, and a cone, if you think about it, it's like, well, the cone is like almost like it's less of a cylinder, right? A cone, if you expanded the cone, this would be a cylinder, this would be a cone. So one helpful way, if you can just remember the 1/3 for a cone, the volume of a cone is the same as the volume of a cylinder, except the cone is 1/3. Michael, trust me, I've been doing this for a long time. I'm a professional teacher, so I've learned how to use my voice without having to drink water too much, at least. And then also other formulas to remember: surface area, the surface area of a rectangular solid. So, for instance, if you picture like a shoebox, for instance, that's an example of a rectangular solid. The shoebox has, if you think about it, 6 surfaces, right? You have the front and the back, the left and the right, and the top and the bottom, right? So the surface area for a rectangular solid, here's the formula for this. But if you think about it, this would be the top and the bottom, length times width. The width times the height would be the left and the right. The length times the height would be the front and the back. So you have 6 sides that are being accounted for in a rectangular solid. And then lastly, one more form actually, sphere, the surface area of a sphere is 4 pi r squared. So notice the formula, this looks kind of familiar, right? Pi r squared is the area of a circle. So if you take it to a 3-dimensional figure, just remember for a sphere, it's not pi r squared, but it's 4 pi r squared. And then lastly, the surface area of a cylinder, right? If you picture, for instance, like a soup can, okay, a soup can. What are the surfaces in the soup can? You have the top circle, you have the bottom circle, and you have, like, if you picture a soup can, like the wrapper, right? Like the paper, if you unfold that paper, that's also another surface. So the 2 circles are going to be 2 pi r squared, and the paper for a cylinder is going to be that other part there, 2 pi r times the height. Okay. So I see a great question just came in. Are these questions reflective of the ACT level of difficulty, or is it more like easy samples? It's a mix. I think some of the earlier questions might be a little bit not quite so challenging. But again, for a lot of people, what you consider challenging might be different for someone else, right? Like I remember when I was doing math way back in high school, I loved geometry for some reason. I did not like algebra quite as much. But maybe you're thinking, oh, the algebra looked a little bit easier than the geometry. Everyone's got different stuff that they focus on. And remember, I mentioned this before, but one thing to remember is that there are no formulas given on the ACT. So you got to remember how to apply these formulas. And lastly, for a cone, the surface area of a traffic cone, pi times r times s, which is the length of the slant. How slanted is that figure? Plus pi r squared. Let's take a look at one more example here to wrap up. Take a look at number 13. Notice it tells us a sphere has this radius of 4, and that's labeled there. Inscribed inside of a cube so that the sphere touches all 6 faces of the cube. Notice, in a cube, it's like a 3-dimensional format of a square. All the sides in a cube are going to be the same. What's the volume of the cube in inches? Well, in order to know the volume of the cube, you need the length times the width times the height. But in a cube, they're all the same. So all you really need is one side. So let's take a look at that sphere. The sphere is inside the cube, but it's inscribed, so it's touching all 6 faces. Well, if the radius is equal to 4, that actually gives us some information here. From the center of the sphere to the edge is 4. What will be the difference from one edge of the sphere to the other edge of the sphere? Well, it's kind of like how you think about circles. It's going to be double that. So the diameter of the sphere is 8, but what else is 8? Each side of the cube is equal to 8, or each edge of the cube is equal to 8. Well, wait a minute. Is it just 8 times 8 times 8? You're right. It is just 8 times 8 times 8. You've got your figure there. The volume is 8 times 8 times 8. Last step, this is where you take out the calculator. 8 times 8 is 64. 64 times 8, please don't do that in your head. 64 times 8 is equal to 512, and choice C is your correct answer. Great work on this question. One quick note, are the diagrams on the ACT to scale or noted otherwise? If not, never assume that the diagrams are drawn to scale, okay? There may be explicit information says the diagram's not drawn to scale, but even then, always go with what information is explicitly given. Caitlin, that was a great question. And with that, thanks for tuning in for our introduction to the ACT math test. We've looked at how to manipulate linear and quadratic equations. We've looked at how to use proportions, ratios, and rates. We've looked at the area of different figures, and we've looked at how to find unknowns in geometry questions. Remember to visit the ACT website at act.org to get extra practice questions on algebra and geometry. So at the top of the hour, so in about 5 minutes, Kristen Russell, who is one of our ACT instructors, one of our very best, is going to take over at the top of the hour and walk through the ACT science test. My name is Arthur. It's been my pleasure to teach you guys. I will stick around actually at the top of the hour to help out with the chat for the ACT science test. So again, we're going to take just a short break. At the top of the hour, we've got ACT science. Don't go anywhere. We will be right back.
Hi everyone, welcome back. My name is Kristen Russell. I know you just had an amazing time with Arthur. King Arthur is my fave, but we're really excited to have you back for the next hour. We're going to focus on the science test section of the ACT. So I want to take a quick moment to talk about what we're going to do for the next hour. We have 4 learning objectives that we're going to be focusing on here. So by the end of this lesson, there are 4 things I want you to be able to do. And I want to just tell you in advance that these 4 things are not only things you're going to be able to use for the ACT, but use in life. You're going to be able to use them for the rest of high school, through college, through grad school perhaps, or in your future careers. So let's talk about them. The first thing we're going to focus on is building a passage roadmap. Now right now you might be like, roadmap? What the heck are you talking about? But don't worry, by the end of today you will know and you'll know how to use it. We're also going to focus on application of the scientific method. So you might have heard of the scientific method today. We're going to go over how it's applicable to the science test on the ACT. We're also going to take a look at some figures, some graphs, charts, and tables. And as Isabella says here, let's be graph-tastic. So we are going to do that. We're going to be looking at lots of graphs today. It's going to be great. Specifically, when we look at those graphs, there are a few things we want to take away. We want to know what's important. We're going to pay attention to those axes, those units, and any trends we could find on a quick glance. Now, before we dive into actually tackling these learning objectives, I want to talk a little bit about the science test itself. So the science test is going to contain quite a bit of different science topics. We're going to see biology, we're going to see chemistry, we're going to see earth sciences, space sciences, and physics. And I know some of you guys, Sabrina's like, I'm very scared about this. I don't know how this is going to go, but that is okay. I don't want you guys to be worried. Although I do have a huge passion for physics, I absolutely love it. You don't really need to know that much about physics to do well for this, okay? So don't panic right now. Most of these questions can be answered just using information from the passage. So we're going to talk about how to critically think your way through the science test. We will not need to know just tons and tons of content for this. The ACT specifically is testing you not on recall, but on your reasoning skills. So again, that's why it's so important that we can use this information we're taking away from today on many things other than just the ACT. We're teaching you how to critically think. All right, so let's talk about what it's going to test you on. There are really 3 major areas that you're going to be seeing tested on the science test. You're going to be seeing data representation. This can be up to 40% of the test, so being graph-tastic, pretty important. We're going to be able to look at these graphs and tables and take away information to get us some points. We're also going to be looking at research summaries. So you guys know there are going to be passages on this section, and we're going to be seeing how different experiments are presented to us. And finally, we're going to be seeing conflicting viewpoints. So that's where we're going to see different hypotheses that are mentioned throughout a passage. So ultimately, if we can follow an experiment, if we can use reasoning skills, and if we can look at graphs and figures, we can do extremely well in this section and extremely well on science classes in the future. So let's take a quick look at what the structure of the test looks like and how the ACT science test fits into that. So it's always going to be the 4th thing you see on the test. This test itself is going to be 35 minutes long, and you're going to have 40 questions. Now, these 40 questions are actually going to be spread out over 7 passages. So some of you guys might be slightly worried about time, but I want to go ahead and reassure you that if you manage your time correctly, you will be okay. So ultimately, this is going to break down to about 5 minutes per passage. Now, I bet some of you guys have certain topics or certain things you like better than others. Have any of you guys ever seen a passage and been like, oh, yikes, that looks really hard. I don't know if I like that one. I think I might want to try something else. This is making me kind of nervous. Okay, so what we're going to do is use that gut instinct. You guys have that instinct built into you. So we're going to use that instinct on the test in the future when we're taking tests to say, this looks hard, let me come back to this. I know lots of you guys over the last hour were asking, can I just guess? You can guess if you have to, and you can move around throughout the test. So we encourage you to find things that look easier to tackle first and save the time at the end to come back to things that look a bit harder. So ultimately, when you see a passage, you're going to take that quick glance. When you start reading a passage, which we're going to talk about how to do today, you're going to want to spend about 2 minutes doing that reading and then save yourself about 30 seconds per question. You're going to see 5 to 7 questions on each of these passages. But again, if you come to a question that looks like it's going to be challenging you, that's stumping you, the graph was just too graph-tastic, then feel free to come back to it later. Now, Ken Gates, I see you're a little worried about how many questions you have in how many minutes, but again, we're going to get so much valuable information in these passages, we're going to be able to fly through these questions. So let's take a look. I mean, we're going to dive right into these learning objectives. So the first one I mentioned is road mapping. I said you guys might think this sounds a little odd. So when you hear the word row map, what comes to mind? And I can guess you guys are thinking map. I don't use map anywhere. I use Google Maps maybe, but physical maps you guys might not see anymore. Well, we are going to make ourselves a physical map here, okay? So the point of a road map is to give us a guide. When you are reading through a passage, there are going to be certain key takeaways that we are going to want to find. So ultimately, we're going to read a paragraph. We're going to try and sum up what we're seeing in that paragraph in just a few words. And fortunately, you're going to have room in your test book to be able to write that stuff down. So we're going to take our pencil, we're going to jot down a couple of words, and we are going to have them for reference to us. Now, what we also can consider is what is the main idea? There's an author of this passage. The questions are going to ask us about what the author thinks and the information in here. So ultimately, we're really treating the science test like it's reading comp that's about science. That's the best way to put it. It's going to make you guys feel way more confident about it. So don't fret. We can do this. Yeah, so Addie's saying here, the science section was so hard, I regret not reading the science passages fully. Well, we're going to talk about how to read them and get the important information. That I'm going to show you how to tackle the questions using those reasoning skills that I know you have. I know you've been using them in your other classes, so we're just going to pull them out of you today. So when you're reading, I want you to think to yourself, what is the point of the paragraph I just read? And the reason you're going to do this is I'm so willing to bet, I would put money on it right now, that you guys have probably read an entire page of a textbook before and then got to the bottom of it and realized, wow, I didn't retain anything. I just read that all. Sometimes you might read it multiple times and be like, wow, I just read that 3 times and I have no idea what it said. This is a great way to stop yourself from doing that so you don't waste time reading but not retaining or engaging with the information. So when you get to the bottom of a paragraph, ask yourself, what was the point of the paragraph? How might this be tested when I get to the questions? This is an amazing strategy. I can tell you, I went to engineering grad school, and when I was in grad school, I did this all the time when reading research articles. It is so, so helpful. All right, so Margot asked, are you allowed to mark the passages? It's like you read my mind, Margot. So we actually are going to write on the text itself. So we are going to underline, we're going to circle any of those things that stand out to us that we might want to come back to later. So when you see this test, you're going to have your passage. You're going to have little paragraph notes in the sides of your margins, and you're going to have underlining, you're going to have circling to reference back to. Now, I'm not telling you that you're never going to go back and actually look at those paragraphs again, but when we get to the questions, if we need to find something, we're going to have a really easy, nice reference to go look for it. So let's try our hand at road mapping. If you're kind of like, road map, I don't use physical maps. I'm going to teach you to do it today. So stick with me as we learn to do this on our first passage. So what I want you to do here is take a really quick look and see what stands out to you on first glance. So we look at this and we're like, I noticed the word blood pressure. I noticed some long paragraphs here. So your gut check would be, does this look like something I would want to tackle now? Now I see a great question from Evan. Evan's asking, should I look at the questions before I read the passage? This isn't really going to be helpful for you. We want to keep our critical thinking hats on, so we're going to read the passage and know what it's about so we can effectively tackle those questions. So we're not really going to look at those at first, but we are going to do our quick glance at the passage itself. Okay, so let's read this first paragraph together, and I'm going to ask you those things about, okay, what's important here? What is the author trying to convey? Blood pressure, the force that blood exerts on the vessels of the cardiovascular system, can be measured using a sphygmomanometer. I'm going to stop right there. Is anyone a little nervous? Sphygmomanometer, what is that? Uh-oh, big word, hard to pronounce. Good news is you don't need to know what it is. You don't need to know how to pronounce it. They were kind enough to give you this little reference, SMM. So what we're actually going to do is highlight that. This is part of your marking up. So for you guys, you would circle or underline. I'm trying to make it stand out really crisply for you. So you would want to underline or circle this sphygmomanometer, SMM, so that if a question uses this abbreviation, you're going to quickly be able to come back and find that within the passage. So we keep reading. We're going to measure blood pressure using a sphygmomanometer and a stethoscope. The SMM consists of an inflatable arm cuff, a pressure gauge, and an inflation pump. So I want you guys to tell me, what is that first paragraph about? If we were going to try and summarize this in just a few words, what's going on here? What was the author trying to convey? Yeah, and Andrew, I'm totally with you. This big word, absolutely irrelevant, okay? We shouldn't be worried about this stuff. They were kind enough to give us abbreviation. We should use the abbreviation. All right, so I see some of you guys like asking about things in the second paragraph. We're totally going to get to those. Don't worry about that. Rachel's saying the variables always mess her up. So if we just think of the variables as things to come back to, we don't need to worry too much about them right now. So I bet some of you guys are thinking, oh, the first paragraph seems to be about how to measure blood pressure. That is the ultimate takeaway if we were trying to jot down just a couple words. So for example here, we see BP measured with stigmo and stethoscope, and we could abbreviate even more if we wanted to. All right, and I like that Nick V here has mentioned that blood pressure cuff. If we need to know the tools we would use for this measuring, we could totally come back to it. Yeah, Rebecca, I'm loving it, how blood pressure is measured. All right, so you guys totally got this in the first paragraph. I'm going to give you a little bit of time to try this on paragraph 2, all right? So we're going to give you guys 45 seconds. In the 45 seconds, I want you to read paragraph 2, and then in the chat, I want you to tell me, what's the key takeaway? What types of things would we want to write in the margin of our notes? And then we can also start to think about which types of things would we want to mark up in the paragraph itself. All right, so 45 seconds. I will see you back here in just a second. All right, that was 45 seconds. I bet you guys were able to get through that. I see some awesome answers coming in here. You guys are pulling out some of these really important key terms. Adrian says systolic pressure. John Gardner says systolic pressure, resting value. Anisha says the process of taking blood pressure. This is awesome. So it starts off with in order to take a measurement. So it's telling us how this is done. It says although, an interesting keyword to kind of tell us the contrast is coming, although the normal flow of blood has no sound, the sound of the subject's pulse disappears when the arm cuff is tightened. So it's going on to tell us what's happening, how we take this measurement. And Paul, you're right, it really isn't that bad if we know what we're looking for. So we keep reading. It tells us about 2 different types of blood pressure we want to pay attention to. So anything we should mark up here? Anything that we might want to underline, circle? Yeah, I know you guys are thinking the same thing I'm thinking here. Systolic pressure, SP, and we might even want to take a quick look at our value, 120 millimeters of mercury. Same thing for diastolic pressure, DP, and our 80. We could also jot these things down in our margin just real quick here, paying attention to those normal values. All right, so Alicia has a great question. Alicia Edwards asks, how are we supposed to be able to understand the passage and be thinking of all these possibilities in only 2 minutes? So I'm going to tell you right now, it does take practice, but you guys were able to get through that paragraph in 45 seconds. It's a pretty long one, and come up with your key terms. So it's read and reflect. Read and reflect. You're just going to get through it and then think about what you just read so you can move on to the next one and get as much out of it as you can. But remember, we're not trying to memorize this information. It's going to be here for us. It's not like they're going to take the passage away from us. We have it right here, just like if you were looking at a book and you were trying to take notes on it. The book is right in front of you. All right, let's take a look at 2 more paragraphs. So you guys are on a roll with this. I'm going to give you another 30 seconds to take a look at paragraph 3 and paragraph 4. So 30 seconds, and I want you, when we come back, to tell me what you saw here in paragraph 3 as the big picture main idea that you'd want to put in your margins. All right, that was 30 seconds. I'm telling you guys, you can get through this pretty quickly. All right, so paragraph 3, what was it about? That's the question you ask yourself. What was this about? Well, when I look at it, it looks like it's about heart rate, and I bet you guys are able to take that away as well. The number of times a heart beats per minute. It's giving us the definition. It's telling us how to measure heart rate. Absolutely, Simone. And we're looking at our normal resting heart rate as being a certain value. Just like the last paragraph we read, these are the types of things we want to jot down in the margins. We can even highlight or underline in some way for ourselves those abbreviations and any of the values given to us. Now, paragraph 4, the structure looks very similar. Very similar. So what's the only thing that changes here? The structure of it's the same. The only thing that's changing is the topic that we're talking about. It's talking about breathing rate, abbreviated as BR. Again, we're getting the definition, we're getting how it's measured, and we're getting our normal values. So we can jot these down and keep on rolling. Now, I see some awesome questions about, well, couldn't we just skip to the graphs? We are going to get graph-tastic today, don't worry. We're going to look at those graphs. But there's tons of valuable information in here. It would be like if you were reading a novel and you skip to the very last chapter. You wouldn't want to do that. There's tons of information we need in here, so the rest of it makes sense. So we're going to be able to put the graphs in context by reading the passage that's given to us. Hannah's on point. Paragraph 4 is all about breathing rate. All right, we got one last paragraph, and we have the table that I know you guys are all very anxious to take a peek at. So what I want to do is give you guys 30 more seconds. In the 30 seconds, I want you to read the 5th paragraph, and I want you to take a very quick look at the table. Now is not a good time to analyze the table in depth and spend a whole minute looking at it, but you're going to take a quick peek at it. So go ahead, take 30 seconds, and we'll be back to see what you got out of paragraph 5. All right, I like it. I'm going to go ahead and tackle this one question here. Krista's worried about not being a fast reader. Let me tell you, I'm not a very fast reader either, and that's okay. Again, we're not trying to read for understanding of this whole thing. So you're going to be reading this more like you would a quick instructional thing than you would if you were trying to memorize tons of details in your biology textbook, right? This material is going to be here in front of us as we tackle the questions. So we just want to take a quick glance and know what's in it so that we have the context built. All right, so yeah, Nick V's like, this is easier than math. See, Arthur had to teach you all this material, right? You had to go back and review all this math. The science section isn't about recall, it's about reasoning. So science is my jam. I love it. And you guys are totally on point. Terry says here, it's looking at the experiments and the effects when we exercise. Yeah, they start out here with to test the effects. You know you're getting an experiment. So to test the effects of different activities, a student administered various tests of function. Now, one thing I like to note here is that we're seeing sequential things in the wording. So we see first, then we see next, then we see finally. So the structure is setting us up here to know what's going on. Max, I love it. You're already thinking we're setting a baseline for ourselves here. So in any good experiment, we have to have something to compare to. So we're seeing the results of this entire experiment in table 1. So in our margins, we would note down real quick, experimental method. This is exactly what we'd expect. We're getting our method. And then once we get our method, the next thing you do in an experiment would be to what? After you know what you're going to test, you run your test, what are you going to do? You're going to take a look at the results. I know it. So table 1 is the results, and we're going to use that information as we move on to our questions. So I'm pretty proud of you guys. You just learned how to roadmap. I know it sounded like it was going to be a challenge, but you nailed it. This is how we want to critically and effectively read. And again, this is not something you can only do for the ACT. This is something I absolutely did on journal articles in my graduate career. So you can absolutely do this later on. Yeah, and Cameron totally noted this. This is very similar to what you would do in a reading comp passage. It's just about the science. Awesome, awesome job. We're on to our first question. This is an exciting moment for us. Okay, so when we get to a question, I want to warn you, it's not a good idea to read every single answer choice because that is a waste of our time, right? We care about reading the question, knowing what it's asking. What we can do is take a quick glance. Oftentimes, knowing what the context of the answers is, how to compare them to each other is going to be pretty helpful. So when I look at this, I see, okay, we're talking about heart rate, breathing rate, and blood pressure. I know those were mentioned in the passage. I know exactly what to do here. So we read, which of the following can be measured with no instruments other than a watch? So I'm going to ask myself, what is this question really asking me? That's half the battle. If you know what the question's asking, you can go research your answer. All right, so I'm seeing a lot of you guys answer in the poll. Keep those things coming in the poll for me. So if we wanted to know how to measure things, we could take a quick glance at our passage, we could take a quick glance at our margins, and we would notice over in those margins that blood pressure measurement was talked about in paragraph 1. If we are talking about our heart rate, that's going to be talked about next. And then we're going to be talking about our breathing rate, so we get all those great things for us. So if we take a look back, in the first paragraph, could we use no instruments to test blood pressure? I'm pretty sure blood pressure was where it was talking about that crazy word, that sphygmomanometer and a stethoscope. So blood pressure only. I don't know about that. Okay, well then heart rate and breathing rate, what did we need? What did we need to measure those? It said something about using your eyes, using your hand, and using a watch. All right, so about 80% of you are totally on board with answer choice D, which is absolutely right. Again, the way we got this information was not by knowing how we measure things, but by going back to the passage and finding this information. There's very little outside material you're going to need to know. You just have to be able to read effectively and find the information that's being asked about. So if we were looking back in our third and fourth paragraphs where it was talking about our heart rate and our breathing rate, we would find that we can measure those with just a watch. All right, awesome job on that first question. I want to keep it rolling here and take this next question up just a notch. Now, when we take our quick glance at these answer choices, we don't see anything stand out quite as much to us, so let's read the question and figure out what it's asking. It can be inferred from the passage that with just a stethoscope, an experimenter listening to an artery in a normal living patient's forearm, it can be inferred from the passage. So we might have to go back to the passage for this. What paragraph did it talk about listening to an artery? Where did you see it talking about listening to an artery? Yeah, I bet you guys are thinking here, well, the first paragraph introduced how I'm going to measure. The second paragraph gave me more detail on that measurement. Okay, so let's be careful here, right? It's easy to get caught up in our thinking, but we need to be careful and stick to what this is mentioning. So F says here, would be able to hear a pulse. Would be able to hear a pulse. Is that what the paragraph mentioned? That's what we got to ask ourselves. Is that what they said to us? Did they say that we would be able to hear this? Yeah, if we go back, which I'm going to go ahead and do right now, we're going to hop back there. If we read through this, it talks about the fact that although the normal flow of blood has no sound, the sound of the subject's pulse disappears when the arm cuff is tightened. So what we can do here is actually listen. But can we hear the blood flowing? Is that what we can hear? Is that what we can hear? Can we hear that? I don't know. It's flowing. It sounded like we needed something else too. Remember that cuff? That cuff was going to tighten our arm so that we would be able to see when the squirting changed. But if we go back and take a look, it told us that if we just had a stethoscope, we would be able to put it on the patient's arm and we would be able to listen. So we would be able to hear that pulse. So if you were not sure, which it's absolutely fine if you did not remember this information, you would want to go back and take a look, okay? Now, Lynn says the squirting of blood sound is from the pulse. This is true, but if we go back and take a careful look at what it says here, it says, as blood starts to squirt through the partially compressed artery, the user will hear a sound and take a reading on the pressure gauge of the SMM. So we ask ourselves, if we did not have a cuff on our arm, would we be able to hear that squirting? And the answer is no. Remember, we have to read the question very carefully. And this question was very clear in that it said with just a stethoscope. So we don't have the cuff. We don't have the sphygmomanometer. We had to ask ourselves, what could we measure with only that? So our correct answer here is we'd be able to hear a pulse. Now, I want to encourage all of you, if you miss this question right now, that is okay. We're here to learn. We're here to develop our skills that we can use on the ACT and beyond. So if this wasn't your favorite question, we're going to see plenty more. In this last learning objective, we learned to roadmap and how to effectively use it on our questions. So next, I want to take a look here at our scientific method. So get ready. This sounded a little more familiar to you guys. So when you've seen scientific method tested in the past in your science classes, it's basically been, okay, what do I want to experiment on? All right, I know what I want to experiment. Let me figure out how to test that. Okay, so I come up with my methods. Once I do the test, I can then take a look at my results. So the purpose of the experiment is the main idea of the experiment you're looking at. What are the researchers trying to test in the study they were looking at? So what specific data are they hunting down? The method. We saw plenty of methods in that last passage right there. The method is how the researchers are going to set things up. So we want to ask, okay, what machinery, what apparatus did they use? Did they change anything? Did they keep anything constant? What types of data were they trying to get? Next, you're going to take a look at the results. So in the results, you're going to see, okay, what trends do I see? Are these results things that I would expect? Is there anything that's unexpected here? What do I think about this data? So we're going to use this last passage. We looked at it before, so we're going to dive right into it. You guys read this already. So it was talking about testing the effects. So tell me, what was the purpose in this experiment? They used the scientific method in this passage. We're thinking about our purpose. I know you guys are totally on board with this because you told me before what they're trying to test. The purpose here is, does what you're doing, does the activity you're doing affect your heart values? We knew that was in the table, so we know that was what they were trying to determine. Now, how did they do it? They gave us the methods. Remember, we looked at the different steps, first, next, finally. So our method was, okay, we're going to test the baseline, then we're going to change the activity, we're going to measure, we're going to test, we're going to record. Finally, we can take a look at our results. So what we saw here were when we were running, we had a higher heart rate and breathing rate. When we're meditating / resting, we're going to see a lower heart rate and breathing rate. And we're going to see that our blood pressure actually stays relatively steady. These are some important things to take away in terms of our results. All right, so now that we understand our scientific method, let's see how we can actually use that reasoning to answer some questions. So question 3 looks a little bit long. I want you guys to take a look at this question stem and tell me if there's anything that stands out to you, like the first thing that you might see. What's the first thing you see here? I see something in all capital letters. I bet you see it too. Which of the following is not a valid criticism of the experimental setup? All right, well, we have to think about what the best way to answer this question is going to be. We know what it says, but we need to set it up so that we are going to successfully be able to think through it. So which of the following is not a valid criticism? So we might decide to approach this as, if I see a valid criticism, I could get rid of it. Okay, so you can rephrase the question so that it's easier for you to understand. All right, so looking at answer choice A, as there was no mention of rest between activities, the reading after meditating may have been influenced by the impact of running on the treadmill. All right, well, let's think about that. We measured the rest right after. When you run on a treadmill, do you think that it's possible that your heart rate might stay up a little bit? Yeah, that sounds like it could be a pretty reasonable thing to take away from this. So again, if we see a valid criticism, we're going to get rid of it because our correct answer is going to be something that's not valid. So we think, okay, answer choice A, no, that's a valid criticism, let's get rid of it. Answer choice B, the very act of administering the cardiovascular test with a restrictive apparatus may have had an effect on the student. Does that sound like it's a valid criticism? Sounds like it to me. The act of administering the cardiovascular test with restrictive apparatus, yeah, that sounds like it could cause a problem. Again, if it's a valid criticism, we can eliminate it. All right, so I know that some of you guys are thinking, well, I don't really know about this, but I see a lot of you polling in. So go ahead and poll in. Take a look at answer choices C and D, our two remaining answer choices. C says, listening to soothing music and meditating are actually two different activities that must be tested separately. Well, let's ask ourselves, what were they trying to do in this experiment? They were trying to get a baseline. They were trying to have someone exercise. Then they wanted to bring them to an even more resting state. So soothing music and meditating were both used for the same goal. Because they had the same goal, we would not consider them two different activities. So C is not a problem. Because C is not a problem, it is our correct answer. Now, if any of you guys are not sure about this and you were thinking D, let's take a quick look. The measurement values were taken only at the end of the activity and may have shown a much greater range of values during the activity. We ask ourselves, is this a valid criticism? Well, this could be a problem. Now, Abby's asking here, what is a valid criticism? So we're asking ourselves, is this something that someone could say is wrong about the way they did this test? So ultimately, we're trying to analyze the design of this experiment. So if you look at this and you're like, yeah, that's something that someone could say was bad about the experiment, then that would be a valid criticism. Absolutely. All right, I'm pretty pumped about this. A lot of you guys were all about answer choice C, so I'm giving you the first pink star of the night. It is my favorite. Awesome, awesome job on question 3. We're going to see lots more questions and hopefully lots more pink stars. So let's take a look. I know you guys were super excited about figures, so in our third learning goal, we're going to dive into looking at some of those figures. So figure interpretation is interesting. I know a lot of you wanted to dive into it immediately. It's important to read the context behind the figures. We're going to look at both tables and graphs tonight. So looking at tables first, it's important to look at the variables of a table, okay? So when we're considering a variable, our first column is usually going to be an independent variable. Now, some of you guys might say, I have no idea what an independent variable is. That's okay. I'm going to tell you. An independent variable is the thing that the researchers or the experimenters are going to manipulate. So it's the thing that is going to be changed. Now that's going to usually be the first column. The table itself is going to show you the relationship across variables. So our dependent variable is the one that we're actually going to be measuring. So one is manipulated and the other is measured. So the units, do you think units are important? In your past experience of dealing with science, are units important? Yeah, absolutely they are. We know that they're super important to give us an idea of what we're talking about. So when we see a table, we want to pay attention to those units. So we want to ask ourselves, okay, are the units on the table itself? Are they presented with the data? Are they presented in parentheses at the top of the column? Or are they in the passage itself? We want to make sure that there's no change of units, so we just need to get a strong grasp on what units are presented. And finally, let's pay attention to trends. Now again, I don't want you to spend tons of time looking at these tables and graphs, but typically you might be able to see a general trend appear to you. So we're going to look for that trend. Do you see any increasing? Do you see any decreasing? Is there anything that stands out to you as you take a look at it? Okay? All right, let's try this. I know you guys are excited about this table, so let's take a look at a question. How could the blood pressure of this student at rest be described? Well, let's orient ourselves with this table real quick. So what we might want to do is take a look at the column headers. So when we do that, we can see the systolic pressure, the diastolic pressure, our heart rate, and our breathing rate all listed right here. Then we have our different measurement points. We have our baseline, we have our 15 minutes on the treadmill, and we have our 10 minutes of meditation. Okay, so we need to ask ourselves here, what do we care about? What information are we trying to look up? We want to know the blood pressure of the student at rest. Okay, so at rest. I think we'd want to look at baseline measurements at rest. All right, it doesn't tell us if we need to look at systolic or diastolic, but if we take a quick peek at our answer choices, we can see that it's talking about both. All right, I see a ton of you guys pulling in. I feel another pink star coming our way. All right, so where would we know what normal is? How would we know what normal is? It's asking us if it's normal, higher than normal. How do we know? Well, I told you you probably don't need to know that stuff outside of the passage. So I'm willing to bet that you can go back to the passage and find it. And sure enough, if we were to hop back and take a look at our normal values, they were mentioned. We wrote them down in our margins. All right, some of you guys are still asking about what's going on with these independent variables. So let me say that one more time for you guys because I know it's an important one. Dependent variables are measured. Independent variables are manipulated. So they're things we change. They're independent. We change them. Okay, so I see tons of you guys pulling in here. So again, we were wanting to take a look at two measurements, our systolic pressure at rest and our diastolic pressure at rest. All right, so then we compare those back to our values. Okay, well, I will hop back and show us those values. We said they were important, and sure enough, they are. They said normal is going to be a systolic pressure under 120. Diastolic is normal if it's under 80. So we need to ask ourselves, is that what those are? Are we under 120 and are we under 180? Absolutely. You don't have to know these things off the top of your head. You go back to the passage, you do your research. I see that 78% of you guys are all about answer choice H. That's it. I love it. Mr. Frederick, you are on point. It is in the paragraph. That's why the paragraphs are there, so we can get it. All right, awesome job. I knew that another pink star was coming your way, so fantastic work on this question. We're going to keep it rolling. I know you guys want to test yourself on some more table information, so let's do it. All right, I see another knot here. Let's pay attention. And Katie, you know, I wish I could sit there with you too, but what I'd rather is teaching you the skills that you can use for the ACT and way beyond. Like, all of these skills are going to be so important when you're in college, and that's what this is for. This is the goal. You guys are going to get into college and use these skills then. All right, so participating in which of the following activities for 30 minutes would not be predicted to result in an increased heart rate in beats per minute? Let's ask ourselves, what are we looking for? So we want to find something that if we participated in it for an extended period of time, we would not see an increased heart rate. Well, if we look at our data, it showed us that being really active would increase our heart rate. So can we kind of get an idea of what we're looking for before we ever look at our answer choices? Man, you guys are coming in with an answer here, but I want you to think about this, right? We want to think about something that's not going to cause an increase. Something that's not going to cause an increase. Well, if we look at our data in our table, what showed our lowest heart rate? What showed our lowest heart rate? So I'm going to go ahead and highlight that column of the table so we can take a peek. Our lowest heart rate is when we were very, very relaxed. Remember, we're looking for the thing that would not cause an increase. So taking a nap on the couch, does that sound kind of like it would be similar to meditation? Sounds pretty relaxing. I really like nap couches or couch naps. Nap couches and couch naps. I like both of those. So I see a lot of you guys are liking answer choice A. Let's just check our other ones real quick. Rowing on a boat. Rowing, that's pretty hard work. I can say from experience that's pretty tough. Walking through the forest. This was initially very popular because you guys were thinking walking's easier than running. But walking is still more difficult than napping. We want the thing where you're not doing anything, where you're being super lazy. So napping on the couch is totally the way we would see our lowest heart rate, or the thing that would not give us an increase. Awesome job. You guys did even better than that one. There has to be something better than a pink star, but it's my favorite, so I'm going to give you another one. Wonderful work. I want to take a look at one more question related to tables, and then we are going to move on to a figure because I know you're super pumped about it. All right. On question 6, we know we're dealing with a table because the question tells us, right? The information's all here. We just need to know what we're looking for. Based on table 1, what conclusion can be drawn about the student after a period of exercise? After exercise. Okay, well, we'd want to think to ourselves, where on the table would I want to look for after exercise? Sure enough, after 15 minutes on the treadmill. I know you were thinking it. Well, we look at this and we're thinking, okay, I know what our normals were. I know some of you guys might be looking at answer choice J and thinking, I don't know. I don't know if I like there's not enough information. But this isn't a trick question. There are no trick questions. We just have to know what we're looking for. So if it asks us, can we draw a conclusion? Let's see if we can draw these other conclusions. F says the student has a dangerously high heart rate. Did the passage define what was dangerously high? Did it tell us what was dangerously high? Brandy, I'm pumped. I'm all about learning. Yeah, it did not tell us. So we cannot make that conclusion. Let's take a look at our next one. Do we know if it's dangerously low? Well, certainly heart rate's not going to be low after exercise, so that one definitely is not going to work. Okay, H, the student is in the normal range for heart rate. The student is in the normal range for heart rate after a period of exercise. Do we know that to be true? Do we know what our normal range is? So a lot of you guys were like, nah, it's never going to be the one where we don't have enough information, but let's be careful. Did the passage tell us about the normal ranges? Like, did they tell us what was going to happen for sure after the student had done this exercise? We're getting votes for everything here. Don't confuse yourself. The information is in the passage for us. I confuse myself all the time, so if it's happening right now, it happens to the best of us, but our goal is to unconfuse ourselves. Okay, so I'm seeing here that there are no votes for G. I'm going to call that a win. No one thinks it's dangerously low. Now we just have to consider, okay, normal range after a period of exercise or high heart rate after a period of exercise. So we know after 15 minutes on the treadmill what these values are, but we do not know if they are dangerously high. So believe it or not, there can be questions where there's not enough information. Okay, this one was super, super challenging. Very, very hard. The reason this is hard is because you guys are trying to think about what you would think about how your heart rate might feel. So just remember that when we're thinking about this, we have to go on the information we're getting. Can we firmly conclude that there would be a dangerously high heart rate if we don't know what the exercise was, if we don't know how long they exercised? Remember, we don't get enough information. So it is perfectly fine to say we don't have the information to make that conclusion. All right, awesome, awesome, awesome. And yeah, Margot is totally on point here. Based on the table, do we have that information? So this question just doesn't give us enough information about the period of exercise to make that determination. All right, awesome. Let's take a look now at our graphs. I know you guys were super stoked about these. So we looked at tables, now we're gonna get graphtastic. So when we're looking at graphs, again, it's all about variables. Nothing really has changed here. Variables are super important to us. So I'm gonna tell you again about these independent and dependent variables so that you guys know what you're dealing with. So our x-axis typically is gonna be our independent variable. So again, this is the thing that we are changing. The dependent variable is the thing that we're measuring. Normally, this is gonna be on our y-axis. So we're gonna pay attention to our axes. So the graph ultimately is just showing us that relationship. Now our units, we said before, these are important. Okay, so what does each tick mark on the axis represent? Okay, well we take a look at that data, okay? Yeah, Josh, I love graphs as well. Now we also pay attention to trends, okay? So our trends are anything that seems obvious to us. Do we have a slope that's always going up? Do we have a slope that's always going down? What does it look like the graph is showing us? Now I know some of you guys are like, man, do I look at the passage? Do I look at the table? It's all about what the question's asking you guys. So if the question asks you, what is your heart rate like after exercise, then you might be able to determine. But if it says something like, what does the table show you? You know exactly where to go. So let the questions guide you. We're gonna do it on this graph too. All right, so I'm pretty stoked for this graph that, I'll be honest with you, first looking at it looks a little scary. It's not, we're gonna break it down. So we're first gonna give you guys 30 seconds. In the next 30 seconds, I want you guys to take a look at your axes. I want you guys to take a look at your units, and I want you guys to take a look at your trends, okay? So 30 seconds on the clock, go ahead, take a peek, and we'll be back to chat. All right, let's take a look together. All right, so when you looked at it first, you'd want to kind of read, right? Did anyone want to dive right into this figure? Be honest, did anyone want to dive right into the figure? I bet some of you did. I bet some of you did. What did we say about giving ourselves context for the figure? Even if you didn't want to, we should read the paragraph first. So the paragraph tells us something important. It tells us what we're seeing here. Solid materials were examined for their maximum solubility levels at various temperatures. The figure shows the grams of solute for various chemical compounds in a saturated solution with 100 grams of water solvent at temperatures between 0 and 100 degrees Celsius. They give us an equation as well. How nice of them. All right, so I see some people already throwing in some amazing trends. Daniel's like, all right, we're looking at temperature as it compares to solubility. Absolutely. So when we look at this graph, we pay attention to our axes. You can see temperature down here at the bottom. You can see solubility here on our y-axis. And we said we want to pay attention to units. So we've got degrees C. We've got grams of solute per 100 grams of water. Now, let me ask you this. What do you think about trends? Go ahead and tell me, what do you think about trends? We saw our variables. We saw our units. What do you see about trends? Aha! Kayla! Morgie Page! I like what you're saying here. You're telling me that when I look at a lot of these, I'm seeing an increase in solubility as I see an increase in temperature. Is that the case for everything, though? Is that the case for everything here? I don't think so. We have to be careful. We have to be really careful. So what we're seeing is that some of these are positively correlated. Most of them are positively correlated, not in every single case. So when I say positively correlated, I mean that temperature increases as solubility increases. So you're just saying your x variable increases as your y variable does. Okay, so let me ask you here. We'll take this back to independent versus dependent variable. Which of the variables are we manipulating? And Michelle asked a great question here. Should we take notes? You can absolutely take notes. Jot down some quick things if there's anything important. A lot of this stuff you can kind of think through in your head as you're reading, but if you see anything really, really important, you jot it down. Carissa, there's no such thing as a stupid question ever. So ask anything you want to anyone you want to, and just try and get yourself more informed. So it's absolutely okay. So stupid question, no. What is a trend? A trend is what we're seeing in the data. So are we seeing that as one thing increases, something else does? Are we seeing as something decreases, does something else increase? So a trend is what the data is showing us. So for example here, I'm going to draw along this. If we take a look at sugar, we can see our line is increasing up here. So as our slope goes up, that means our temperature increases as solubility does. Now what we're going to do for simplicity's sake here is give these guys some nicknames, because I know some of you guys are like, I don't know what these compounds are called. The good news is you don't need to. Some of you might be familiar with the fact that this one right here that I underlined in red is called potassium nitrate. You do not need to know that for the science test on the ACT. So we're going to call it Cano. We're going to call it Cano. We're not going to call it gnome like you would actually pronounce it if it was a word. We're going to call it Cano for fun. We're going to call this one that I am underlining in green nano, okay? This one that I am circling in green, we're going to call nabber. Below that, we're going to call it kibber, kissel, naso, and CISO, okay? Because you do not need to know what these are, so that should not worry you as you're going through. So we've taken a look at our axes, we've taken a look at our units, we've taken a look at our trends. Now we're ready to move forward, okay? Let's see if we can answer some questions. All right, quick glance here. I noticed that we have some of these compounds in our answer choices. We have kissel, we have nabber, nano, and Cano. Those are fun to say. Which of the following solutes shows the greatest increase in solubility as the temperature increases from 0 Celsius to 100 Celsius? So our first step here is going to be like orienting ourselves with our figure. So it tells us that we should be looking at temperature increasing from 0 to 100. And we want to know which of these shows the greatest increase in solubility. We can make an awesome prediction here. What are we looking for? How should we orient ourselves on the figure? Yeah, Cano's pretty special. Cano's pretty special. I like that you guys like the name. And when I look at it on the graph, it looks kind of special too. Why does Cano look so special? Why does that look so special here? If we take a look at Kano, which I love you guys, and you're hilarious. So you guys are like, I need to know this for the test. Absolutely, add a W onto that bad boy. So Kano here is interesting. Kano shows us the steepest slope. Steep slope. What does that tell me? That shows that I'm having a large increase as I'm seeing an increase in temperature. So greatest slope is going to correspond to greatest increase. So I saw that on the graph. I take a look. I try to find that in my answer choices. Sure enough, it's there. Oh my gosh, we had a serious runaway winner here with answer choice D. I saw some special requests for gold stars. So I'm going to be honest with you, I am all about pink star, but I aim to please. So gold star for 98% on question 7. You guys killed it. All right, let's take a look at another one, and so I can say some more fun words here with all of these compounds, because I am loving it. All right, question 8. Looking at our answer choices here, we're not seeing the compounds. We're seeing more trends. All right, which type of solute, according to figure 1, so we know it's all about figure 1, has a lower solubility at higher temperatures? Okay, so where on the figure would we want to look? Where on the figure would we want to look if it tells us high temperatures but low solubilities? So immediately I'm looking here, I'm like, well, high temperatures, that means I need to be really far to the right, and low solubility tells me I need to be low. So I'm thinking like right in this area. Okay, so high temperatures at 100, I'm looking at the graph and I'm seeing Naso and Kissel are at the bottom, okay? Naso's at the very bottom of our high temperature, so that tells us at 100 degrees, which is the high temperature, I'm seeing a low solubility. Okay, well, I don't see Naso in my answer choices, so I gotta be careful here, and I also have to be really careful about the trends I'm seeing. So Kissel has an upward trend at the end, whereas Naso has a downward trend. So Naso is actually lower. Yeah, we're looking at the bottom of this thing. So the lowest one at the highest temperature is Naso. Okay, so we might say something that has sodium or something that has sulfate. Again, we don't have to know what those are because the answer choices tell us. So we look at answer choice H and it says sulfates whose formulas contain SO4. Naso, which was our prediction, has an SO4. That is going to have our lower solubility at our higher temperatures. 92% of you guys killing it with answer choice H. All right, I want to look at one more question, okay? This is going to be the hardest one we're going to look at tonight, so get ready for it, but I know you guys can do it. Question 10. Approximately how many grams of nano could be dissolved in 25 grams of water at 90 degrees C? Our answer choices are numbers. Let's be careful here. Well, we know what we're looking for. It tells us 90 degrees C in the question. Okay, so I'm going to tell myself, let's look over at 90 degrees on the graph. All right, so I do that. Now, again, it wanted to tell me how much can I dissolve. So I'm going to look at 90. I'm going to go up to nano, which my mark that I'm going to pay attention to is right here. And then I'm going to flip over to the y-axis. So is it 160? Is that it? Is that it? Looks like it's there, but are we missing anything in the question stem? I see lots of you guys like J. Let's go back and make sure we know what we're looking for, because if we answer the wrong question, yikes, not good. So it says, how much can we dissolve in 25 grams of water? Remind me, what was the unit for solubility that was actually given to us in this figure? Remember, we paid attention to it before. If we take a peek back, it tells us grams of solute per 100 grams of water. 100 grams. Wait a second. This says 25 grams. Ooh, let's think about that. Okay, so if it's 160 at 100 grams of water, but now we want 25 grams of water, we've taken a quarter of it. A quarter of it. Well, I think we should probably take a quarter of 160 then. So all we have to do at this point is say 1/4 of 160, and our correct answer here has got to be answer choice G. I saw a lot of you guys switching your answers over. So again, 160 does stand out if we don't finish the question. So it's our first step, but we need to take the quarter to get to our correct answer. All right, I'm going to give you guys one more gold star before we wrap it up here because that was very, very strong work. So the last thing I want to talk about today is really how much we accomplished. You guys did an amazing job in the last 2 hours. The first hour with Arthur, King Arthur, my fave, on math. Then you hang out with me on the science. So we tackled 4 main learning objectives. We created roadmaps, so you guys know how to do it now. We talked about the scientific method, so you know how to read about an experiment, which is awesome. And we got super graphtastic. I love that you guys came up with that name. I'm going to use it all the time now. We learned how to tackle questions by reading graphs and tables appropriately. So amazing, amazing work tonight. You guys did awesome. If you want to check out more questions, make sure you guys go to www.act.org for more science and math questions. And feel free to join us back here on May 22nd as we take a look at our other sections for the Intro to English Language Arts. So awesome job tonight. Thank you to all of you. Thanks for Liz and Rob as well. They kept the chat rolling. Have an awesome, awesome night. Thank you so much for joining us.